Okay, so today we're going over noble gas notations. And if you remember from a while ago, we went over the noble gases, and that's always going to be the right-hand or most right-hand column of the periodic table, group number 18. So the noble gases can basically be used to write an electron configuration, but in a shorthand form, so you don't have to like write out the whole thing. So these are the steps to writing down a noble gas notation. First thing you're gonna do is you're gonna find the noble gas that comes before the element that you're trying to write the electron configuration for. So you choose the noble gas that comes before the element, and then what you're gonna do is you're gonna write the noble gases symbol in brackets, and then you just write out the rest of the electrons, the rest of the electron configuration of the remaining electrons. So it's going to kind of look like this. So let's go over this example with silicon. So silicon is atomic number 16. So I'm going to write out the original electron configuration first. So you would have 1s2, 2s2, 2p6, 3s2, 3p2. So this would be the normal way to write out the electron configuration. And if you want to do the noble gas notation, what you do is you basically look at silicon and again, choose the noble gas that becomes before silicon. So the row before would be neon. So I'm going to write out neon and put the symbol in brackets. Actually, I'm going to do it over here so we have more space. So neon brackets. And then after neon, I'm going to write out the remaining electrons until I reach silicon. So after neon, you would have 3s2. And then you would have 3p2. Okay, and that would be it. So the noble gas notation is a lot more simpler and easier to write out. And the reason why this works is because if you look at neon's electron configuration, it actually is the exact same thing as the full electron configuration for silicon right here. So since neon basically matches up with whatever we were going to write down for silicon anyways, we can just write out neon and then write the remaining electrons. So a lot shorter and a lot easier than writing out the entire thing. So let's move on to the next example. Here we have argon, and argon is itself a noble gas. So even though you have argon as a noble gas, you can't just write bracket AR and finish. You still have to write out or choose the noble gas that comes before the element. So even though argon's a noble gas, the noble gas that comes before argon would be neon. So I'm going to write out bracket neon. And then I'm going to just keep writing out the electron configuration. So I would have 3s2. And then this would be 3p6. So this would be argon's electron configuration. Okay, so let's try astatine, which is atomic number 85. And for these ones, like writing out the full electron configuration isn't too bad. But for astatine, imagine you had to write out the entire electron configuration starting from the beginning all the way to 85. That would take forever. So that's where noble gas configurations become really useful. So again, choose the atomic number that, or the noble gas that comes before your element. So that would be xenon in this case. So I would write bracket Xe. And then I can kind of start moving in. So this would be 6s2. And then over here, we would have 5d. But if you look here, actually, what happens is if you look right here, so 5d1, 57, And then it starts breaking up. So it doesn't go directly from 57 to 72. You have to actually go into the F block this time. So you would have 57, and then 58 would be right here. And if you look at 58, it's in the 4F block. So this would be 58 all the way to 71. And then you would go from 71 to 72. So there's kind of like a section that it breaks off into. So this is the 4F section. So you would write 4F, and then you would count how many electrons there are here. So if you count them all, this should be 14 electrons. So this would be 4F14. And then if you go from 71 and then back to 72, we're back in the 5D section. So this would be 5D. You would have 9 electrons left over. So 5D9. And then to finish up, we need to reach AT. So we would be in 6P, and it would be 6P 1, 2, 3, 4, 5. And technically, you're not supposed to like leave these separated. So what you would actually do is you would rewrite this. So you would write it out where you would have the 5Ds kind of like in one spot like you normally do. So you would have Xe or xenon, 6s2, 4f14, 5d10, 6p5. And that would be your electron configuration for astatine. Okay, so why don't you guys take some time? Let me launch this poll, and you guys try the next 4 on your own. Okay, so let's go over these. Sulfur is atomic number 16. So again, choose the atomic or choose the noble gas that comes before it. So that would be neon. And then if you just keep continuing on, you would have 3s2, 3p1, 2, 3, 4. And then for neon, again, this is one of the ones where it's a noble gas, but choose the noble gas that comes before it again. So you would have helium. And then 2s2, 2p6. Titanium would be over here. It's a transition metal. So titanium, the noble gas before that would be argon. And then you would have 4s2, 3d2. And then lastly, lead, which is Pb, is over here, atomic number 82. So again, choose xenon, because that's the noble gas before lead. And then I just go in order. So I would have 6s2, 4f14, 5d10, and then 6p2. Okay, let's move on. So electron configuration of ions, we can skip. I'm going to start now moving on to the quantum model. And again, the quantum model is going to be a little bit confusing because it's very conceptual. So I would say unless you're planning on taking AP Chem, you don't have to worry too much about the quantum model. I'm still going to explain what it is so you guys can kind of see why we're doing electron configurations and what it actually means. But if you feel like you don't understand it fully, you don't have to worry, and you can always just check back at your notes during, like, if we're taking a quiz or a test anyways. But if you are planning on taking AP Chem, then you do have to know this, and you'll probably go more in depth into it next year anyways. Okay, so what is the quantum model or the quantum mechanical model? The quantum mechanical model is our current and most accurate understanding of how an atom is structured, specifically based on its electrons. And the reason why it's the most accurate is because unlike the Bohr model, The Bohr model, remember, was a two-dimensional model. So like, let's say I draw the Bohr model for boron. You have the different electrons surrounding your atom, but this is very flat. It only shows it in a two-dimensional area, whereas the quantum model is a three-dimensional model. And that should be more accurate because atoms in real life, they're three-dimensional. They're not just flat on a piece of paper. And what the quantum model describes the atom as, or the electrons in an atom as, is electrons contain or move around in orbitals. So remember, like I said last time, the Bohr model just describes electrons moving in kind of like a circle orbit, like the planets revolving around our sun. But that's not how electrons actually behave. So electrons actually move in all these different types of shapes. So like for the 1s orbital, the electrons in the 1s orbital would be moving in like a sphere. A 2s orbital, electrons would be moving in a bigger sphere. And then when you get to the p orbitals, the electrons move in kind of like this dumbbell or like a figure 8 shape. So they're moving in these three-dimensional shapes. And the reason why this works is because electrons are kind of like I kind of think of them as little flies that always just buzz around. They don't stay in one place. They're moving around not only in a circle, but in like this general area, just moving about all the time. So the orbitals are the three-dimensional region around the nucleus that indicates the probable location of an electron. So it indicates where an electron is most likely going to be. And how scientists figured that out was they mapped out and saw something called the electron cloud. So if you look here, you can see this is actually an s orbital. And how I know that is because it's sphere shaped, right? You can see it kind of looks like a sphere. And this shows the probability of where the electrons in this s orbital is going to be. So if you look here, right, this darker area, that's where the electrons were found more often. So most of the time, or more likely, the electrons are going to be kind of here, and then sometimes they'll be kind of spread out. But if you take a picture of it overall, over time, you can see it turns or looks into this sphere shape. So that's how like electrons have shapes or orbitals. It shows the probability of where they're most likely going to be. Okay, so the quantum mechanical model is going to use quantum numbers. And these are just 4 pieces of information that can tell you exactly where an electron is going to be. So like I said last time, right, if you're trying to find where a location is, you have to look at like an address. So if we look at like Glenn Wilson's address, you can have the state, the city, the street, and then the apartment or street number. So in the same way, the quantum number will give you 4 different, or the quantum mechanical model will give you 4 different pieces of information, and each of them is going to be more and more specific about what the electron and where the electron is. So the first quantum number is known as the energy level, and that's the principal quantum number. And this is one we already know, right? Basically, it tells you how far the electron is from the nucleus. So energy level 1 would be closest to the nucleus. Energy level 7 would be furthest from the nucleus. Your energy level will also describe the size of the orbital. So for example, if you have a 1s orbital versus a 2s orbital, a 1s orbital may look kind of like a small sphere. So a sphere that kind of looks like this. Whereas a 2s orbital, since it's in energy level 2, it'll be an even bigger sphere, right? Because it's a further energy level than the 1s orbital. So it'll kind of look like this. So you can have the same orbital shape, but the energy level will tell you kind of how big it is. Okay, and then the next quantum number is known as the angular momentum quantum number. And that's why I was kind of saying, like, don't worry too much about the specific definitions or like the specific terms. You don't have to really memorize them. Just look back at your notes because they're just like such random words. I mean, I'm sure the scientists have a good reason for why they named it this way, but it's not that intuitive. So the angular momentum quantum number is known as the sublevel or subshell, and that describes the shape of your orbitals. So like I was saying, s orbitals look like a sphere. And remember, these are all three-dimensional. And then your p orbitals will look kind of like a dumbbell shape or a figure 8. And then your d orbitals look like this. And then f orbitals, don't even worry about it because they look like super crazy. So I would say the main ones to just recognize are your s orbitals, the sphere-shaped ones, and then your p orbitals, the dumbbell-shaped ones. Okay, and again, where your electron is determined by, or what shape the orbital is determined by like the electron configuration and which electron you're talking about. So you have S, P, D, and F, and that corresponds with the different blocks on your periodic table. Okay, and all of these will always match up to your periodic table. The next quantum number is known as the orientation, and that's the magnetic quantum number. And that basically tells you like the axis of the orbital. So when I see the word orientation, I think of like x-axis or y-axis or z-axis. And we have to come in terms with the z-axis because we're talking about 3D objects this time. Usually in math, you only talk about X and Y, so like on your paper, but Z-axis is the one going into your paper and out of your paper. So your S orbital, you can see here, it only has one orientation. And that's because your S orbitals are sphere shaped, right? So if you have a sphere, you can't really like be more on the X-axis or more on the Y-axis or more on the Z-axis. Spheres are like symmetrical throughout all the axes. So it's only going to have one orientation. It's going to take up or take a space in all three of the different axes, X, Y, and Z. When you get to a p orbital, however, since they're kind of like dumbbell shaped, they can lie along one of the axes. So like this is the 2px orbital, which lies on the x-axis. This orbital or this 2p orbital lies on the y-axis, and this orbital lies on the z-axis. So for your p orbitals, you can have three different orientations. So you can have x, y, and z. So px, py, pz. So three different ways that your p orbital can kind of lie on. And this is just like, I guess, extraneous information, but your d orbitals would have 5 orientations, and your f orbitals would have 7 orientations. And that's because these two have like weird looking shapes, so they can kind of like rearrange themselves in different manners. But that's why I said they're kind of complicated, so you don't have to worry about it unless you take AP Chem or you take like chemistry in college. And then the last quantum number is going to be known as the spin quantum number. And that just tells you which directions your electron spins. So even when we have our Earth, right, it rotates around the sun, but it also spins every day. And that's why we get like day and night, right? Day is when you're like the side you live on of the Earth faces the sun, and then night is when it faces away from the sun. So in the same manner, electrons will also spin. So they're known to either spin up or down. And usually electrons will pair with opposite spins because they can kind of balance each other out and stabilize each other. So you'll always have an electron that's spinning up and an electron that's spinning down. And that's also why when you see me draw like a Bohr model, you'll often see me draw it in terms of like the electrons as pairs, because one of them will be paired up and the other one will spin down. So I always pair them together. And it's also just kind of like easier to see. Okay, so I know that was like a lot of information, but again, don't worry too much about it unless you're going to take AP Chem. Let's go into how to create an orbital diagram. So an orbital diagram is a visual representation of the electrons of your atom. So once you draw the orbital diagram, you'll basically be able to know like not only the energy level and the sub level, but you'll also be able to know the orientation and the quantum number, so and the spin. So like if it's spinning up or spinning down. So these are the steps to creating an orbital diagram. It's going to seem confusing at first, but once I do a couple for you, it should kind of make sense if you go back to it. So step 1 is you write the electron configuration of your atom. Step 2 is you write the energy levels and sublevels out. So it's just saying kind of the same thing as step 1, writing out your electron configuration. Step 3 is you're going to draw boxes or lines to represent the orientation of each sublevel. And again, this is kind of the part that gets confusing when you just read it, but once you like do a little bit of practice, it'll make sense. So each orientation of your sublevel can fit 2 electrons each. So s orbitals will have 1 orientation, like we said above, because they have to be in all the axes. And then p orbitals will have 3 orientations, d orbitals will have 5 orientations, and then f orbitals will have 7 orientations. So I'm going to literally just draw out the lines or boxes. So 5, and then f orbitals would be 7. So you'll see what these lines, or some people use boxes, you'll see what these are used for a little bit later on. And then step 4 is you're going to have 1 electron that's always spinning up, and then another electron that's always spinning down when you pair them together. Okay, so let me go over these 3 principles, and then we could do some of the practice to draw an orbital diagram. The first principle is known as the Pauli exclusion principle. And then this is kind of like the fancy, or not fancy, but the technical term of it. So it says no 2 electrons can have the same set of quantum numbers. So all that means is if you have an electron in the same orientation as another, they can't have the same spin. So like I was saying before, electrons, they like to pair up in opposite spins. So this would be like the incorrect way to write the orbital diagram, because here you have 2 electrons that are both spinning upward. The correct way would have been if you have 1 electron spinning up and then the other electron kind of spinning downward or pointing downward. Okay, so electrons with opposite spins will always have to pair up. You can't have 2 in the same spin pairing up together. The next principle is kind of redundant. It's just saying, so it says electrons will always occupy the lowest energy level available. So all that's saying is your electrons will fill in the order of the electron configuration table, because the electron configuration table is written from lowest to highest energy. So for example, if I'm writing the electron configuration of, let's say, like boron, right? So the correct electron configuration would be 1s2, 2s2, 2p1, right? 1s2, 2s2, 2p1. So it's saying just don't skip your orbital. So you can't just skip around, because that means your electron is excited. So like, let's say I wrote this as 1s2, 2s1, 2p2 instead. This would be incorrect, right? Because even though you have the same number of electrons, you have to fill them up in order. So lowest to highest energy. And here you can see this is like a visual representation. So you have your nucleus here, and then your 1s orbital. So you fill the 1s first, and then 2s, and then 2p, 3s, 3p, 4s, 3d, 4p, etc. So just basically follow the electron configuration table. Okay, and then the last thing before we start our orbital diagrams is if you have multiple orbitals of the same energy, so or of the same, if you have basically multiple orientations in the same energy level, you have to put an electron into each one of them before you pair them up. So if you look here, right, you see this orbital diagram is the correct one, because I have 2 electrons in the 2p sublevel, and you could see I fill up each separate orientation first before I pair them up. So this would be incorrect because I'm pairing them up before I start to spread them out. So don't pair up your electrons until you have at least 1 in each orientation. Okay, so let me show you what that means. We're gonna draw the orbital diagram for phosphorus. And if you ever get confused, you can always just also look back at this chart, because this will basically tell you how to draw and fill in your orbital diagram. So make sure you remember, look at this chart right here. Okay, so orbital diagram for P, the first thing that I'm going to do is write down the electron configuration. So I would have 1s2, 2s2, 2p6, 3s2, and then I would have 3p3. Okay, and then now I'm going to draw lines or boxes representing each orientation of my sublevels that I have. So my S sublevels, so 1s2 has just one orientation, right? So all my s orbitals have one orientation. And then when I hit a p orbital, remember you have three orientations, one of them in the x-axis, x, y, z. You don't have to write x, y, z, but that's just showing like which orientations they are. And then your 3s2 orbital has one orientation, and then your 3p3 orbital would have three orientations. Okay, and if you forget what number of orientations you have, either look back at the notes right here, or again, you can just look at this chart. This chart tells you how many of each that you have. Right? Okay, so then now I start filling in my electrons. So 1s2, that means you have two electrons. So you just literally draw two arrows, one that's spinning up, another one that's spinning down. Okay, same thing for 2s2, right? One that's spinning up, another one that's spinning down. When you get to the p orbital, that's where it gets a little bit trickier. So you just have to make sure you fill them up in order. And what I mean by in order is you follow the rules for Hund's rule and the Pauli exclusion principle. So remember the Hund's rule, it says if you have multiple orientations, fill them up separately first before you can pair them up. So if I was filling this correctly, I would fill it up like this. Fill up each separate orientation first, and then I can start to pair them up. So for this one, like it doesn't really matter which way you fill it because it has every electron complete, but I just want you to make sure you get in the practice of filling it up correctly in order. Because if you don't, then you're gonna mess up when you get to like the ending. So 3s2 has two electrons. So again, pair one up, another one down. And then this is what I mean. So 3p3, it has three electrons. So that means you would fill 1, 2, 3. So you would have to fill out each orientation first. And then that would be your orbital diagram. If I filled it up like this instead, so if I filled it up, so if I have three electrons and I filled it up like this, right? I paired it up before spreading them out, that would be wrong because that would be a violation of Hund's rule. So make sure you fill them up separately before you start pairing them up. Okay, and then I'm gonna do the same thing for iron. So iron's orbital diagram. Before I do that, let me write out the electron configuration. And for iron, I'm actually going to use the noble gas notation so I can make it shorthand. So iron is over here. So its noble gas notation would be AR 4s2 3d6. So let's start writing it out. So for orbital diagrams, when you write it in the noble gas notation, you don't have to like actually draw out any of the electrons because you're just assuming that it's the same thing as argons. So I would have argon, and then 4s2 would have one orientation, and then this is the 3d sublevel, so that would have 5 orientations. And again, it says that right here, d orbitals have 5 orientations. Each box fills up 2 electrons each. And then also you can look here in case you forget. And that's why, like, if you count, it should always match up to your periodic table, right? So like, for example, it says d orbitals have 5 orientations and each one can fit 2 electrons each because one spins up, one spins down. So that's a maximum of 10, which should match up to your periodic table because here you can always count, right? Your d block always can have a maximum of 10 electrons. So same thing with your p orbitals. It has 3 orientations each, which is a maximum of 6 electrons, which will match up with your p block over here. And same thing with your s and f orbitals. Okay, so let's draw this orbital diagram. So 4s2, so one spins up, one spins down. And then 3d6, again, fill them up separately first. So I would have 1, 2, 3, 4, 5. And now that I've filled up each orientation, I can now start pairing one up. So that would be my 6th electron. So again, this would be the incorrect way to do it if you did it like this, because you have empty orbitals or empty orientations here before you start filling up, before you start pairing them up. So this would be incorrect. Okay, so let's do this example. This example is a little bit easier than the ones I have in your quiz and your other practice, but I'll kind of tell you guys what your quiz is, or what your quiz and your lecture assignments are like today after we go over this. Okay, so these ones are pretty easy. You can see, right? You just kind of look at the last part of the orbital diagram. So this would be 2p2. So if you look here, 2p2 would be carbon. And then same thing for element B. Here we have 3p4, right? 4 electrons. So that would be 3p4, sulfur. But you can see they did these orbital diagrams correctly because they put them in separate orientations or orbitals first before they start pairing them up. Okay, I just want to go over one more thing. So again, if you like, the quiz is more kind of like this one, where I'll like have an orbital diagram that's either correct or incorrect, and I'll say say the reason why this orbital diagram is correct or incorrect, or state the rule that violates one of these orbital diagrams. And then I just want to go over like the examples or the exceptions to the electron configuration rule. So remember, I went over last time, chromium and copper are exceptions to the electron configuration rule. And anything in that same column as chromium and copper too. So like MO, silver. And I'm gonna go over silver just so you can see like why that is. So if I draw out silver's electron configuration, that would be, so silver would be krypton, 5s2, 4d9. But remember, a d orbital that's like half filled or completely filled is more stable. So what would happen is you would have one electron that would leave and go into the 4d orbital. So Ag or silver's orbital diagram or electron configuration would actually be 5s1 4d10. And the reason for that is if you draw out the actual orbital diagram, you can like visually see what's kind of going on. So you can see here, if I drew it normally, so this would be 5s2, 4d9. You can see there's one electron that's missing here, but you have all these electrons here. So you just literally need one more to make all these electrons stable. So again, what's going to happen is this electron from here would actually move over to the 4d orbital to make it 4d10. So it's just better to make all these electrons stable by having like a completely filled 4d section than just having it over here and only having one 5s orbital stable. Okay, so just remember chromium and MO and then copper Ag, those are kind of like your exceptions to the rule. So I'm just telling you guys that in advance for your quiz. Okay, so that's pretty much it. Finish up the lecture notes and the quiz and you guys will be good for this week. And there's no test next week. I'm planning for the test to be the week after that. So I'll tell you guys more about it on Tuesday. Okay, bye guys. I hope you guys all have a good weekend.